group. So we're almost there. We proved this local result, which is up on the board at the end of the last lecture, and so today we'll finish off by proving a global version, and then we'll look at other topics. Just very briefly, I'm not sure whether I'll have time to get through all. Hang on, I missed out something important. Applications. That was the whole point of doing this thing. Applications to G-complete reducibility. And then other topics, non-connected groups. I've just talked very briefly about how you modify the formalism when your group G is non-connected productive group. Non-algebraic closed fields. So practically nothing is known here. This is a nice area for research. There are all sorts of unsolved problems. Then I'll talk about a problem, the question of Kuhl's hammer. Colin mentioned work of Kuhl's hammer in her lecture yesterday, I think it was. So I'll talk about a problem of his, which is relevant to G-complete reducibility. Then some applications to finite groups of Lie type. I'll talk briefly about a problem involving maximal subgroups of simple groups of Lie type. How you can use some ideas from G-complete reducibility to bound this number. And then last of these topics is some applications. Going back the other way, we've seen applications of geometric invariant theory to G-complete reducibility. I'll finish with some applications of G-complete reducibility to geometric invariant theory. So let's finish off this proof. What are we trying to prove? Just let's recap. So we had a G module V. We have a point in V, that's little v that's unstable, and this means that the origin is an enclosure of the orbit, and this means that you can take little v to 0 by taking the limit along an appropriate co-character. And then we wanted to measure how quickly co-characters take v to 0. So if you take a maximum torus T, then we make sense to talk about weights. And if we take a co-character lambda that takes values in this maximal torus, then we define this numerical function mu v comma t with lambda, which is the minimum over, you run through all of the weights and support. So here, support of V consists of these weights, and we call this psi I lambda. And then we observed that because these functions are Z linear, we can tensor everything with the real numbers and work with real vector spaces. So we get a function I don't need the lambda now. So this gives us a function from yr of t to reals. So yr of t was the z module y of t tensored with r. And then the observation was that actually we don't need the t in here, but this gives a sensible function on the whole of y of g, in fact y of g with r. this is the function that we wanted to optimize, and we needed to normalize our co-characters. So we have this length function yr it sends a co-character to its length norm, and so this gave us a norm in the usual sense on each of these real vector spaces yr of t, and also the other property that we wanted is this length function is that its conjugation invariant. Okay? And then one of the results that we proved yesterday that we will need is that so now we define f of lambda, it's mu v of lambda of the f is in the function yrg and we saw that this was invariant undertaking positive scalar multiples of the argument. And then the other property that we wanted is that f of u dot lambda is equal to f of lambda for every lambda and for every u in the unipolar radical p. We're going to use this property today. So this I think was 5.8. Yes, 5.8. So that's where we were yesterday, and we proved the restriction of f on each of these subspaces, on each of these vector spaces. So this t subscript here is just supposed to denote the restriction of this function to this attains maximum value, which we call CT, and the set of points where it attains this maximum value is a ray. So it's a array the origin. So it's an array, not including the origin because f is not defined at the origin, and the result also told us that this array contained at least one of these integer points, just 1 point. So you think of the whole board as y. Oops. Not t. So it contains this value on array r and this ray contains one of these integer points, and lambda t is the one that's closest to the origin. Okay? So that pretty much summarizes where we finished last time. And then there's a comment at the top here that I rushed over quickly. That's just saying that you we do see one of these points in the ray, but I don't prove that. Okay, so now to finish off with, and this is the theorem that gives us the uniqueness and existence of this lambda opt and this p opt. This theorem 5.11. F attains its maximum value. So if you have an arbitrary real value function f on some space, and of course it might be unbounded, or it might not, but even if it's bounded, it might not actually attain its maximum. So this function attains its maximum value. Let's call this value c. When I say it attains it, it means that it actually takes that value. So we'll take that value at some lambda opt. If you remember right back early on towards the start of the previous lecture, we were thinking of this more generally for a G module, for a G variety, capital X, and I was talking about the optimal destabilizing cocharacter lambda opt X. Here we're looking at the special case of a V module, so I'm calling the points in the V module a little bit. And this is an honest cocharacter. And lambda opt is unique to RUP lambda opt conjugacy subject to the condition that its length is as small as possible. So here's the global result that we want. How are we going to attain it from these local results? The local results which tell us something for each maximal torus. Let me draw a picture. So this C here is just going to be the largest of all the CTs. So CT is the maximum value that this function attains on a particular maximum torus T. There are infinitely many maximal tori, nonetheless you can show that there are only finitely many values CT. So you just pick C to be the largest of them. Okay? Now the problem is that the C might come from two different maximal tori, right? We might have a maximal torus P1, and we get this lambda T1 from this local result. So this is the point where f has its maximum when we restrict f to yr of T1. And then associated to that, we have a parabolic subgroup. And now the problem is that this might happen in some completely different maximal torus, T2. So we do the same thing in T2, we get a lambda T2 and a P2. So let me draw a picture. But I'm going to draw these pictures overlapping. There's a reason for that. So here we have T2, and here we have lambda T2. It's a theorem, a standard theorem in the theory of reductive algebraic groups, that P1 intersect P2. The intersection of any two parabolics contains some maximal torus. So sitting in this intersection, we have a maximal torus T. And we have lambda T. Okay? For uniqueness, we want to show that lambda T1, lambda T, and lambda T2 are the same. Well, not the same, but the same after conjugation in the unipotent radicals. And so what we're going to do is use the fact that this black thing and this green thing are two maximal tori of a parabolic subgroup, so they're conjugate. Any two maximal tori of an algebraic group are conjugate. So we can conjugate this lambda t1 and put it in this green maximal torus. Okay? And it's going to turn out that because of 5.8, you don't change the value of f when you do that. So I'm going to move this guy, put it all the way over here. F is going to take the same value at lambda t, and this guy I've moved. Therefore, they must be the same by the uniqueness of the local maximum, okay, and by this minimality condition. So that's going to tell me that the black guy and the green guy actually coincide. And then I can do the same thing with lambda t2, and I'm going to see that when I move lambda t1 and lambda t2 into here, they become equal and they become equal to lambda t, and that's going to give me the result that I want. Because it turns out that when I'm moving them, I'm just conjugating by something unipotent radical. Okay. So that's the idea of the proof. So first of all, this is what I started by saying. You look at the maximum value of all the CTs, and I've got a little CT there, haven't I? That should be a capital CT. You can show there's a largest one, and so that is obtained at some lambda opt. And so what we need to show, as in the picture, is if we have two different maximal tori and the corresponding lambdas for those maximal tori both give you this maximum value. So we show these are maximal tori and f of lambda t1 equals f of lambda t2. Then lambda t2 is in its conjugate to the other guy by something in its unipotent radical. And let's call P1 lambda T1 and P2 T2. And in fact, let's call lambda 1 equals lambda T1 and lambda 2 equals because if you can show this, then the uniqueness follows, because in particular you can make this guy equal to your lambda opt, and then that shows that any other lambda where you attain this maximum value is conjugate to lambda opt by something unipotent radical of lambda opt. And now the proof goes as in the picture. We have some T that's contained in P1 intersect P2. If T is a maximal torus of G, then certainly it's a maximal torus of any proper subgroup of G. So T is also a maximal torus of P1 and P2, and then by conjugacy of maximal tori, T1 and T P1 conjugate. So G1 dot lambda 1 is the co-character of T, the sum G1 and P1. But now actually we want to replace this G1 by a U1, where U1 is not just in P1 but in the unipotent radical of P1. And we can do this because we can write G1 is equal to U1 L1, where the U1 is in unipotent radical and the L1 is in the Levy subgroup associated to lambda 1. Okay? And remember, this Levy subgroup is the centralizer of the image of lambda 1. So when you conjugate lambda 1 by this L1, you're not actually doing anything. Yeah? So G1 lambda 1 is equal to U1 L1 lambda 1. But L1 dot lambda 1 is lambda 1, so we get U1 dot L1. Okay? now by 5.8, which I've carefully left on board. 5.8 f of u1 dot lambda 1 is equal to c. It's equal to, well, I should put in the extra step, equals f of lambda 1, which is equal to c. And now observe that c is the largest value that f can possibly take on yr of t. Why is that? That's because c is the global maximum of f on the whole of yr of g. So certainly it will be therefore be the global, it will be the maximum on this subset. We must have c of ct. Right? This is the largest value that the function can possibly take anywhere. Therefore, in particular, it's equal to the maximum on yr of t. Okay? So now we have two co-characters in y of t, if both attains this same maximum value, and we can conclude that, therefore, that u1 dot lambda 1 has to be equal to lambda t. Okay? There's a little bit more argument that's needed. Actually, this argument tells us that u1 dot lambda 1 and lambda t have to lie in the same ray. But then you use the fact that lambda 1 and lambda t are both supposed to be minimal. They're supposed to have the smallest length possible to deduce that these are actually. Okay. And now you just do exactly the same argument for lambda 2. But if you conjugate a co-character by something in the unipotent radical of the associated parabolic, you're not changing the parabolic. So p of lambda 1 is equal to p of u1 dot lambda 1. So u1 is in the unipotent radical. What happens in general if you do this? If you replace p lambda with pg dot lambda, then the parabolic you get is replaced by g p lambda, g inverse. But so if u1 is actually in the parabolic already, you're not changing anything. This is equal to p lambda 2, and this is equal to p lambda t, and this is equal to p lambda 2 by the same argument with an extra step in here, like this one. So if the parabolics are equal, they have the same unipotent radical. And then lambda 2, how do you get from lambda 1 to lambda 2? Well, you can get from lambda 1 to lambda t in one hop, conjugating by u1, and then you can get from lambda t to lambda 2 by conjugating by u2 inverse. And I think I've got that the wrong way around up there. Yeah, I have. So this should say u2 inverse. It's funny how you only see these mistakes when you're standing up front talking. I must have read through this at least 3 times. And this completes the proof. So this gives us the existence and uniqueness of our optimal destabilizing parabolic. Now that's not quite the end of the story, because we wanted to know that the stabilizer of this point B GV stabilizer should be contained in this optimally destabilizing parabolic. And that follows from this more general observation that if you replace V with G dot V, then you end up conjugating the optimal parabolic. I'm not going to prove that, but if you just chase through all the constructions that I described, then you'll see how they transform when you conjugate by G. So for instance, we showed that we showed that mu of G dot B, mu G dot B of G dot lambda is mu V of lambda. This is something that we showed. Well, actually, we didn't show. You're going to show as one of the exercises. So chasing everything around, you see it transforms nicely, and then in particular, this result will follow. So that was quite a long and difficult argument, I think. You sat here very patiently. Now we're going to reap the fruit of this hard work and prove some applications to G-complete reducibility. I can rub this stuff off now, I don't need this. Theorem. Suppose we have an H inside our G and a normal subgroup N of H. If H is GCR, then N is GCR. So a normal subgroup of a GCR subgroup is GCR. And now we have this optimal destabilizing parabolic to play with. The proof is pretty easy. So suppose H is GCR, but N is not. So we're going to get a contradiction. Well, if N is not GCR, then we have this optimal destabilizing parabolic P opt of N. Okay. So N is in P opt of N. This is way back from theorem 5.1. This was this application of this optimal destabilizing parabolic formalism to GCR subgroups. So that the normalizer of N is contained. This was the point. This is what we wanted. But H normalizes N. H is contained in the normalizer of N. So this P opt of N is a parabolic subgroup that contains H. But P opt of N is a witness that N is not G completely reducible. So what does that mean? That means that N is not contained in any Levy subgroup of this thing. But H is larger than N. So H can't be contained in any Levy subgroup of this thing either. And that tells us that H is not GCR, but that's a contradiction. N is not contained in any Levy subgroup of E opt. So H is not either. Gives us a contradiction. Therefore, N has to be GCR. So see how easy the proof is once we have this optimal destabilizing parabolic. And then this remark up here is just saying that this is a generalization of Clifford's theorem from representation theory. Okay. Our next result. Subgroup G, then the normalizer, the centralizer, are also GCR. So we run into problems here And the problems that we run into are that this group and this group might be non-connected, and this makes them difficult to handle in our formalism, because we want to talk about parabolic subgroups of this and parabolic subgroups of this, and I haven't explained how you make sense of that if the groups are non-connected. So what we're going to do is just pretend that they are connected, or to be more precise, we'll just look at the identity component. So we're proving something weaker. Why is this weaker? If ng of h is GCR, then so is ng of h naught, because this is a normal subgroup of that. Okay? So by the result we just proved. So I'm proving something slightly weaker, but you can make sense of all this stuff for non-connected reductive groups as well, as I'll discuss briefly later on. Suppose normalizer of h naught is contained in some parabolic. So the first part of the proof doesn't actually use the optimality, so I could have proved this back in section 4 before we've done all this stuff. But the proof for the centralizer of h, so we're going to prove this for the normalizer of h, and then we get this for the centralizer, because the centralizer is normal in the normalizer. That's how the proof's going to work. And for that we do need the optimality. Well, oh no, this is okay. Yeah, normalizer of h naught. Yeah, I have a problem, don't I? Because I'm just looking at this. So let's assume, in order for this argument to work, I need to assume that h is connected as well. I hadn't spotted that. But again, this is actually not a restriction. We can make the argument work. So why do I need this? I want h to be contained in the normalizer of h naught. That's why I wanted to say that h is called, which is indeed. But h is GCR, so this means that h is contained in some Levy subgroup of P. H is contained in some Levy subgroup. And now we say, now let's think of this in terms of co-characters. We can write P in the form P lambda and L in the form L lambda for some co-character. It's saying that h is contained in L lambda. L lambda is the centralizer of the image of lambda. So if h is contained in L lambda, that's saying that lambda centralizes h. H is contained in L lambda, so the image of lambda centralizes h. That's saying that lambda we can regard as a co-character of the centralizer of h. And the centralizer is contained in the normalizer. And actually it's a co-character of the identity component. I'm not doing anything I should be here, because the image of a co-character is connected. It's either a zero-dimensional or a one-dimensional choice. Okay? So now I have a connected reductive group ng of h naught. So this is reductive. We proved this back in section 2, I think. We proved that this is reductive. So it makes sense to talk about P lambda of this group. This is a connected reductive group. And we saw what happens when we go into a subgroup. If we have a co-character of this connected reductive subgroup of G, then P lambda in the smaller group is just P lambda in the bigger group intersected that group. But this is the whole of NGH. NGH naught contains P lambda. So we have a co-character of this connected reductive group, and the associated parabolic subgroup is the whole thing. Okay? Now that's quite a special thing. In general, P lambda is a proper parabolic subgroup. If the parabolic subgroup that you get is not proper, the only way that can happen is if this co-character is actually central in here. Okay? So another way of seeing this, which is what I've put up there, is that this parabolic subgroup is its own Levy subgroup. So remember our original characterization of Levy subgroup, maximal connected subgroup of the parabolic. So if the parabolic subgroup is the whole thing, then it's reductive. So the maximal reductive subgroup is that thing itself. Okay. So the normalizer ng of h naught is contained in L lambda. But this is what we wanted to show. We wanted to show that ng of h naught is GCR. We wanted to show if it's contained in a parabolic, then it's contained in the Levy subgroup of that parabolic. That's what we've just done. Therefore, ng of h naught is GCR. It's like a little game, this kind of argument. I must have done arguments like this dozens of times, so I'm very familiar with them. It takes a little bit of getting used to this point of view, thinking of the way these parabolic subgroups and Levy subgroups and co-characters interact with each other. But once you've done this kind of thing a few times, just you don't have to think so hard about how to do it. And then, as I said, centralizer is normal in the normalizer. So the centralizer is also GCR. And that's the end of the proof. So now if you stick these two results that we just proved together, then you get that corollary there, 5.16. If you have a subgroup H of G, it will be GCR, if and only if it's normalizer. The next result, proposition 5.17, says, oh, you can read it there, take a GCR subgroup S of G, and take a subgroup of the centralizer of S. Remember, we've shown that the centralizer of a GCR subgroup is reductive. So this CGS it's at least a reductive group. Maybe it's not connected, but at least it's reductive. And then the result says that if you have a subgroup of this reductive group that's CGS, which is CGSCR, then it's GCR. And I left the proof of that as an exercise. But again, as we did in the previous proof, replace CG of S with CG of S naught, just so you don't run into problems with non-connected reductive groups. So let's just pursue this idea slightly further. So the content of this remark our subgroup S and take the subgroup H at the centralizer. Then H, C, G, S, C, R implies that H is G, C, R. That's the argument that's the result that I just said that you won't prove. The converse holds if S is linearly reductive. So if, for instance, S is a torus. So this applies in particular to Levy subgroups because any Levy subgroup is the centralizer of the torus. Any Levy subgroup is the form L lambda. It's the centralizer of the image of lambda. The image of lambda is a torus. So you can recover from this result of Serre that I mentioned a while back, that if you have an H contained in a Levy subgroup L of G, then H is LCR if and only if it's GCR. I didn't write that down because this is we have this result. So this is true if S is linearly reductive, but it's false in general. So that's the first half of the paragraph. Maybe we'll have our 5-minute break now, and then I'll finish this paragraph, and then that will just about bring us to the end of these applications. All right, are we starting?
Yes.
To mention one application of this result here in the linearly reductive case. So let's suppose that P is not 2, and let's consider a special orthogonal group sitting inside the special linear group. So the special orthogonal group is actually the fixed point set of an involution. Okay? The involution is not actually living inside here. You need to go to a non-connected group. So define an automorphism of SLN by phi the matrix A is the inverse transpose of the matrix. Okay, and then the special orthogonal group is the fixed set of this because a matrix is orthogonal if and only if it's equal, its transpose is equal to its inverse, yes? And so let S be the cyclic group generated by phi. So this is just a cyclic group of order 2 because this is an involution. And let G be equal to the semi-direct product. So this is, well, one can show quite easily that this is an algebraic group. So this is a non-connected reductive algebraic group. And as I said a moment ago, the fixed point set of the centralizer, if you like, S in G, the identity component anyway, is S over N. If you take the full centralizer, you're going to pick up this finite subgroup S as well.
Yes, and G.
What have I done?
S is only C.
Oh yeah, not yeah. Thank you. Thanks. Now this subgroup is linearly reductive. Because it's a finite group whose order is not divisible by the characteristic. So applying this result up here. So if H is contained in the special orthogonal group and the characteristic is not 2, then H is SON completely reducible if and only if H is SLN completely reducible, which, as we know, means that H acts completely reducibly or semi-simply on K to the n. So this is nice because in general it can be quite difficult to tell when a subgroup of some arbitrary connected reductive group is G completely reducible or not, because you have to mess around with parabolic subgroups and Levy subgroups. This says that as long as P is not 2 and you're looking at the special orthogonal group, it's enough just to look at SLN, where like this is here. And then we get an analogous result for symplectic groups. You've got the symplectic group SP2N inside SL2N. So let's finish by looking at an interesting problem. Oh, one thing I didn't say when I was talking about the first paragraph here before the break. Suppose S is G completely reducible and H is contained in the centralizer of S. Then H is CG of S completely reducible if and only if the product HS is G completely reducible. This makes sense. This is because H and S commute with each other. So this is a subgroup. So we're going to look at this problem in a little bit more detail. Suppose G has a pair of GCR subgroups that commute with each other. Is the product GCR? Is that always the case? So that's what we're going to finish by discussing. So that's the problem that's written up there. The question H1, H2, GCR and commute with each other. Product GCR. And the answer is yes for SLN and GLN. This is an argument of Rudolf Tanger, who kindly gave us this argument and let us put it in our paper. So this is a question of representation theoretic nature. You can frame this in terms of representations. If you have representations of two groups H1 and H2 and their images commute, then this gives you a representation of the group H1 cross H2 in an actual way, and then you can ask if the representations of H1 and H2 are completely reducible in the usual sense of representation theory. Is the representation of the product completely reducible? We asked some representation theorists this question, and none of them seem to know, which we thought was surprising. This seemed like this would be a very standard kind of question in representation theory, and that the answer would be in every standard book. But people didn't seem to know the answer, and so as an open problem, I think this is a nice open problem because it's very concrete, and maybe someone can come up with an answer for this quite quickly. If we take a pair of subgroups in SLN and GLN, okay, so take a pair of G completely reducible subgroups, or if you like, completely reducible representations. Now let's weaken the hypothesis slightly. Instead of assuming that H1 and H2 commute, let's just assume that H1 normalizes H2. Is H1 H2, which again makes sense if H1 normalizes H2. This is GCR. So again, this is what looks like a fairly standard representation theoretic looking question, but none of the people that we asked knew the answer. So if any of you can work it out, or if you know some representation theory and you've seen this somewhere, would be very interesting to know. Okay, so if you have this for SLN, then you also have it for SON and SP2N if the characteristic is greater than 2 by the result that I just discussed, because being completely reducible in SON and SLN are equivalent. So if you ask this question for SON instead, you just put everything inside SLN and you know what the answer is, as long as P is at least 2. And similarly for SP2N. And so this actually lets you answer the question for the classical groups. As long as P is greater than 2, then the answer to this question is yes for any classical groups. Or any group, all of whose simple factors are classical. You have to go through this process of first you prove this for simple groups and then you stick them together to make arbitrary reductive groups. Remember, a reductive group is isogynous to a product of simple groups and a torus. You also have to worry about the different forms, simply connected or adjoint. So if you have this result for SLN, do you also have it for PGLN? And the answer is yes, because as we saw in an earlier result, G complete reducibility is well behaved under isogenies. So if you put all this together, and then you use all this wealth of detail that Liebeck and Seitz generated about subgroup structure of simple groups of exceptional type, they have these tables of subgroups and what their centralizers look like. You put all this together and you prove that the answer to the question is yes if P is good for G, or even if P is greater than 3. Remember that for G of type E8, 5 is actually a bad prime, but it turns out that the prime 5 doesn't cause you any problems in type E8. You look at these tables of Liebeck and Seitz, they say the subgroups of a simple exceptional group of a certain type, F4 for instance, as long as the characteristic is greater than such and such, these are what they look like. So you play around with that and you get the result. But the answer to the question is no in general, because Liebeck gave an example with P equals 2, as you might expect, and G is symplectic. So he found a pair of connected reductive groups that GCR and commute inside G, but their product is not GCR. And he also very kindly let us put this example in our paper. And by the remark that we had on the previous page, if H1, H2 is not GCR, this shows that H1 is not CGH2CR, and vice versa. So this is indeed showing that the opposite direction to the problem. The problem was if H is contained in CGS, is it true that HGCR is equivalent to H CG of S CR? And the answer is yes in one direction, and then this is a counterexample in the other direction. Okay, so that ends this section on applications. Now I'm going to talk briefly about various topics. So the nature of the Oh, it's just slow. Let's have a think. Ah. Yeah, here we are. That's the page I want. Stay there. Okay, we'll briefly discuss a range of other topics. Non-connected groups, I don't say anything very much here at all. What do? You just do exactly what you did before. You just use exactly the same definition for P lambda as you did before. And we call the groups that we get this way, well, they're not, the difference is that this does, it still makes sense to talk about parabolic subgroups of non-connected productive groups. But this class of groups gives us something slightly different. We call these Richardson parabolic subgroups, in honor of Richardson, whose name has been cropping up a lot in these lectures, or our parabolic subgroup for short. And we define L lambda exactly the same way as before, the centralizer of the image of lambda, we call this a Richardson-Levy subgroup. And now we define G complete reducibility just as before. H is G completely reducible if whenever it's in some side some R parabolic subgroup, it's contained in some R Levy subgroup of that R parabolic subgroup. So everything goes through much as before. There's a little bit more fiddling that's needed, because you have to worry about whether these P lambdas are connected or not, or if they're not, how many connected components they have and stuff like that. So in particular, we've used several times the result that a parabolic subgroup is self-normalizing inside a connected reductive group. This is no longer true if you go to non-connected groups and look at P lambdas, but you can replace that result by the following observation. This result down the bottom here. So P lambda intersect G naught is equal to P lambda G naught in the notation that we had before. This is a parabolic subgroup of G naught. So these P lambdas, any group normalizes its identity component. So any of these P lambdas normalizes some parabolic subgroup of G naught. And then the result here says that if you have any parabolic subgroup of G naught, then its full normalizer inside G is one of these R parabolic subgroups. So this result lets you get around the problem that parabolics are not always self-normalizing. So anyway, let's move on. Magic. What about non-algebraically closed fields? There's a whole theory of this stuff for non-algebraically closed fields. In fact, when Serre first introduced the definition, he was working over an arbitrary field. So let's take an arbitrary field of positive characteristic. Definitions make sense in characteristic 0 as well, but let's take a positive characteristic, and let's call K bar the algebraic closure. Take a connected reductive group defined over K, and a K-defined subgroup H. And we just repeat the definition, but putting these K's in front of everything. So K parabolic subgroup equals K defined parabolic subgroup. So what does this mean? So roughly speaking, you can think of it this way. You have some variety defined over K, just K to the n, and then you can say that a subvariety is K defined if the polynomials that define it for you, remember a variety will be the set of zeros of some polynomials. If the polynomials that define it for you all have coefficients in this subfield K. Okay? So you can look at the point of view that's taken in Borel's book, is that you can think of K to the n as sitting in K bar to the n, and then if you have some subvariety of K bar to the n, it's defined by some polynomials and then you ask, are the coefficients of those polynomials, do they lie in that small field? And if so, you say that the subvariety is k defined. That's actually a lie. There's a subtlety that I'm leaving out. But, I'll just ignore that. What I just said is true if the field is perfect.
So solutions that they can the algebraic closure, solutions of the polynomials.
Ooh, I don't want to talk about it. Think of all of the solutions. Think of all of the solutions in the algebraic closure, but somehow remembering the fact that the defining polynomials come from k. Okay, this has caused me and my collaborators some problems. There are two different formalisms for approaching this. There's Borel's, which is the one I'm using on this slide because I think it's a little bit more digestible for people who haven't run into these ideas before. And then there's a more modern formalism, which you'll find in the recent book on pseudo-reductive groups by Conrad, Gabor, and Prasad. A lot of people think that this Borel formalism is old-fashioned. We've had a lot of complaints from referees that we've been writing our papers in this old formalism. They're saying, no, you must write it in this new formalism. And your results are all wrong because you've written it in this old formalism. I'm being a little bit unfair, but this clash of formalisms has led to some misunderstanding. Okay, referees. So this definition makes sense. So the point here is that if you have H contained in G, and if you think of all of this as living inside the group over the algebraic closure, then you can look at all of the parabolic subgroups that contain H, and some of them will be k-defined, and some of them won't. Yeah. So you can ask, is H GCR over K, and then you're just looking at the k-defined parabolic subgroups that contain H. You can ask, is H GCR in the original sense, and then you're looking at all of the parabolic subgroups, all of the k-bar defined bars. Okay? And even if you have a k-defined parabolic subgroup that contains H, it might be the case that H is contained in a Levy subgroup of that parabolic, but not in any k-defined Levy subgroup of that parabolic subgroup. So there's this question, is H being GCR over K, is this equivalent to saying that H is GCR? And because of, for the reasons that I've just explained, the answer is no in general in both directions. But of course there are many situations where the answer is yes. It's like this general problem we've been talking about a lot of an H inside an M inside a G is being MCR equivalent to being GCR. No in both directions in general. Yes under all sorts of special situations. It's the same here. Well, one nice thing, if your G is a general linear group or a special linear group, then being G completely reducible over K means exactly the same thing as before. It means that the representation that you get is completely reducible over K. So any K-defined stable subspace has a K-defined stable complement. And so the example that I'm getting you to work out in the exercise sheet is a very simple example involving a cyclic group generated by a 2x2 matrix. So you should be able to do the calculations without too many problems. So this stuff down the bottom is just saying what I just said. It makes sense to ask if you have an H. You can ask, is it GCR over K, or is it GCR meaning GCR over K? Or more generally, you can do this. You don't have to go all the way up to K bar. You can go to any algebraic field extension. So if the field is perfect, then things are quite nice. So for instance, H is GCR over K, if and only if it's GCR. So if the field is perfect, that means that most of the time you can just pretend that your field is algebraically closed. Like is good. So remember, the field is perfect means that if you're in a field of characteristic P, raising elements to the power of P, that's a field automorphism. Because in characteristic P, x plus y to the power of P equals x to the P plus y to the P. This mistake that all of our undergraduate students make when they're expanding brackets. Well, my undergraduate students make, I don't know about yours, is actually true in characteristic P. And the field is perfect, that means that this map is surjective. Yeah, sorry, in general it's only injective. The field is perfect if it's surjective. But the field is not perfect, and what's an example of a non-perfect field? Take the finite field with P elements, which is perfect, and look at the field of rational functions in one variable. That's not perfect because the P fruit of T is not. But it is in the algebraic closure. And so there are various nasty things that can happen. As I mentioned, exercise 3, I'm asking you to work out an example. An example in the other direction, with an H that's GCR but not just GCR over K, is basically it comes out from the same calculations or similar calculations to the one, an example 2.11 we talked about before. No particular reason why you should remember what 2.11 said. 2.11, so I'll remind you, P equals 2, G of type G2, you had an H inside, an M inside G, H was a type K1 cross A1, H was S3, H was GCR, but not MCR. And the reason why you had the problem here was boiled down to the fact that H is not separable inside G. And this same non-separability tells you that a subgroup closely related to H is GCR, but not GCR over K. And the reason is that you kind of have problems taking square roots of things in this construction. So here's an open problem. So theorem 3.12. This was the theorem that if you took a point x and applied a co-character and got a limit x prime that was in the g orbit of the point that you started with, then it was in the RUP lambda orbit of the point that you started with. That's what theorem 3.12 says. And then I mentioned as an open problem, is this true over an arbitrary field? So that's connected with this stuff here. Here's another open problem. Is the centralizer of a GCR subgroup, of a subgroup that's GCR over K, also GCR over K. My PhD student, Tom Hiro Uchiyama, I gave him this problem to look at, and I assumed he'd be able to polish it off in a couple of weeks once he'd mastered all of the kind of necessary background. I thought this would be an easy problem, and I thought the answer would be yes. And he kept coming back to me and scratching his head and producing these interesting examples. So at one point he produced this interesting example, which is actually essentially the same as the example I've given you on exercise sheet 3 with this 2x2 matrix. And the point there is that you see unipotent elements which are not unevenly triangularizable. And so he never solved this. He never solved this problem. He could prove the answer is yes in some special cases. I kind of suspect now that the answer is no. But one problem that you have in this problem is that what I've written down doesn't even make sense, because in general the centralizer of a K-defined subgroup need not be K-defined. This kind of awkward. This awkward fact. Maybe I should, maybe I should just take a subset of K bar to the n. Suppose it's the set of some zeros of polynomials with coefficients in K. And I said before, well, a subvariety like that is K-defined. This is what it means to be K-defined. This is not quite true, and the subtlety is that you form the ideal generated by these guys. But now if you look at the ideal of all functions that vanish on X, it's not actually just this I, it's the radical of this I. And what you actually need is for the radical of I to be defined by polynomials with coefficients in K. And this is not always the case if your field is not perfect. It might happen that these FIs will have coefficients in K, but when you take the radical, you need polynomials that don't have coefficients in K. So that's what's going on there. Even though it's fairly easy to see that the centralizer is the set of zeros of some polynomials with coefficients in K, when you take the radical, things might go wrong.
What are the special cases on there when the answer is yes? Like the field is
Well, if the field is perfect. If the centralizer is reductive, then there's an argument. So one way of proving this in the algebraically closed case uses this result of Richardson that I mentioned briefly, which is that the centralizer of a GCR subgroup H is reductive. And that came from a result of Richardson that said that if you have a closed orbit, then the stabilizer of a point is reductive. And then if you know that CG of H is reductive, then you can talk about P lambda of CG of H, and you can say things. Also, surprisingly enough, he can prove it if CG of H is unipotent at the opposite extreme. And the reason for that is that if you have a unipotent group, then there's no way of putting co-characters into it. You have to have, because if you have a non-trivial co-character, then you have to have, say, a one-dimensional torus. And the result is true then also. But in general, it seems to be very tricky. Okay. Let me move on to the next thing. Well, we might have time to get through all of these. This is just this scratching the surface of all of these topics, and there are no. I'm not going to present any proofs or complicated calculations. So back in 1987, I think it was, Kuhlshammer asked the following question. Well, here's the general context for the question. In characteristic 0, if you take a finite group, it has only finitely many isomorphism classes of complex representations of dimension n. This is Mashka's theorem. This is a very standard result in the representation theory of groups. The same thing is true if you replace GLNC with an arbitrary reductive group G, and instead of looking at isomorphism classes, you look at homomorphisms. From F into G. So here F is finite. This is a finite union of G conjugacy classes. If the characteristic doesn't divide the order of the field. Okay, it's very on Mashka's theorem. And moreover, the image of every homomorphism is G completely reducible. What happens if you allow P to divide the order of the group? Then things go really, really badly wrong, because as we've seen, hom CP cross CP into SL2 in characteristic P is an infinite union of conjugacy classes. Well, it's kind of clear that this is bad because it's a P group. So what happens if you control the behavior on the P subgroup? Or for a more general finite group, what happens if you control the behavior on a CeLO P subgroup? Does this get rid of this wildness? So here's Kuhlsammer's question. Fix a homomorphism from the CeLO P subgroup to G. Look at homomorphisms from F to G, whose restriction to this CeLO P subgroup is conjugate to this fixed thing. Is it true that there are only finitely many conjugacy classes? This is a very reasonable attempt to try to control the behavior. The answer is yes. And GKN, that's a new group. GLNK or SLNK. Fairly simple representation theory proof. It's just 2 or 3 sentences. Slaughterby showed that the answer is yes if P is good. However, the answer is no in general. Our old friend example 2.11, if you modify this construction slightly, then you get a counterexample. Although we didn't see this is not in our original paper, we didn't see this until what, 5 or 6 years afterwards. All you had to do in the construction was change one of the parameters from 3 to any odd prime that's not 3, and you get a counterexample to Kuhlsammer's question. And then you can interpret what's going on there in terms of this non-abelian cohomology that we've discussed briefly. And so here's a nice open problem. Are there any counterexamples with P of all of the constructions that we know for P equals 2? In the appendix to Slaughterby's paper, which is it's in the list of references there, there's another example of cram, which predates the counterexample I was just talking about, but that's for a non-connected, non-reductive group. Kuhlsammer asked the question more generally for an arbitrary linear algebraic group G. And then I mentioned this connection with G-complete reducibility. If you're going to get a counterexample, then you need to be able to construct infinitely many conjugacy classes of homomorphisms from F to G. But this theorem 2.13 says that there are only finitely many conjugacy classes with G completely reducible image. So if you want to get a counterexample, you need to be working with homomorphisms whose image is not G completely reducible. Otherwise, there's no hope of being able to generate infinitely many conjugacy classes. Okay, next topic: finite groups of Lie type, simple groups of Lie type. I thought it might be nice to mention this in this audience, since I know a lot of you are interested in finite group theory. And the simple groups of Lie type are, as Alan said yesterday, in some sense the main source of finite simple groups. So how do you make these guys? Take a simple algebraic group. The word algebraic is in there, so it's not to be confused with finite simple groups of adjoint type. So take a Frobenius map. So if G is SLNK, then your sigma and characteristic P, then your sigma could be just raising the matrix entries to the power of P. Or more generally, raising the matrix entries to some power of P. Yep, and this gives you a family of finite interesting finite groups, SLN and Q. Yep. And here's a result. Take a finite sigma stable subgroup of G, in particular a subgroup of G sigma, the fixed point set, but F doesn't actually have to be fixed by sigma, it only has to be stabilized, then at least one of the following holds: F is G completely reducible, or F is contained in a sigma stable proper parabolic subgroup of G. Now, what this is heading for is results to do with bounding the number of maximal subgroups of these finite simple groups of Lie type. So if your group is inside a parabolic subgroup, then it's kind of very easy to understand maximality behavior that's going on. If something is maximal but it's inside one of these parabolic subgroups, then it must be inside the maximal parabolic subgroup. This finite group of Lie in an appropriate sense. And it's quite easy to understand what you've got there, and it's also easy to count these guys. So either you're G-completely reducible or you're in a sigma stable proper parabolic subgroup. And the idea of the proof is that if F is not G-completely reducible, then it's inside this optimal destabilizing parabolic. And the naturality of the construction, I suppose is the way to say it, tells you that this P opt should be stabilized by any automorphisms that are lying around, including not just conjugation. So that was the observation that this P opt contains the centralizer in G, yeah, but also under these Frobenius endomorphisms. If sigma is just standard Frobenius raising to the power of Q, then that's kind of clear to see what's going on. If sigma involves a graph automorphism as well, slightly more complicated. And then it gets more complicated still when you have these funny isogenies which swap long and short roots. The argument is a bit more complicated. And then the application of this is a bounding number of maximal subgroups. So pick a group of Lie type, finite group of Lie type of rank at most R. I never said this before, perhaps I should have. The rank of a reductive algebraic group is the dimension of a maximal torus. And this makes sense because all maximal tori are conjugate. So when you fix the rank of G, then that means there are only finitely many possibilities for G, essentially. And then fix an N, which you want to be the size of your subgroup gamma, then the number of conjugacy classes of maximal subgroups of order most N inside this almost simple group, which is essentially a finite simple group of Lie type, is bounded by a function of N and R only. And so what's the point of this? The point is that you could put some F inside SL in Q, by which I mean SL in finite Q elements. And you can say, count conjugacy classes of homomorphisms from F into this group. So homomorphisms. And you can count SL in Q conjugacy classes. And of course you get a finite number, because this is a finite group. But as you let Q get bigger and bigger, this finite group gets bigger and bigger and bigger. So maybe this number of conjugacy classes just grows in an unbounded way. So the point of this is to show that you get some bounds on the number of conjugacy classes that do not depend on Q. That's kind of the point of what's going on here. And that's the content of this remark down the bottom. If you're in case A of the proposition, so you're looking at G completely reducible subgroups, we know that from this theorem 2.13 that if you write it like this, so by this I mean homomorphisms from the finite group F into G whose image is G completely reducible is a finite union of G conjugacy classes. And you use this finiteness here to give you your uniform bound up here and tell you that things don't go too badly wrong when you let Q get bigger and bigger and bigger. You use this together with Lang's theorem. I did have a little bit more to say about geometric invariant theory, but I'm out of time, so I'll stop here. Thanks very much for your attention.
So
Thank you very much for the class. Are there any further questions or remarks? Otherwise, before I let you go enjoy the coffee break, I have an announcement. There is an idea of implementing all the notes with also solutions to the exercises. So if you would like to contribute to this, please send your solutions in any form, PDF, scan, or whatever, to the organizers. Thanks. And I suggest we thank Ben again. So we resume at 10 to 12, 11:50.